Like I said, I've been here. I was here like 3 or 4 years ago. And thanks, Sean, for inviting me, by the way. I always forget to do that. And I gave a talk somewhat related to this. And then Bill's given us colloquium. And I know he gave a seminar last year. But it will be different flavor, I guarantee you. Okay, so today we're going to talk about, I'm going to start the story with surfaces with pi 1 isomorphic to the free group on 2 generators. All right? Sean's favorite one. I knew I'd be okay when I did that. So basically what you have is, since it's the free group on 2 generators, you have 2 loops, right? You say, here's one loop and here's the other loop, like that. And you want to think about all the possible surfaces that you can get from there. Okay? One way to do this is to just flatten out the surface and see what happens in the interior here. And what you do is you kind of fill this in. Okay? Oh, wait, so go around like this. And then what's going to happen is that the surface, that's going to be the fatter part of the surface, and then there's going to be, I want to be able to connect those things. So, and let's talk about how to connect those. All right? So that's the general idea, but now let's draw 4 of them. Okay, so we have the happy little ghost. Okay. I know I have 4 because okay. And these are called ribbon graphs. And as you see in a little bit why they're called ribbon graphs. They look like little ghosts, I don't know. Okay, so one of the ways to do this is just to take a ribbon and you want to connect these, right? You want to make it so that you go through this and you just connect them straight like this. Okay? Right? You take these ribbons right here, and here's your surface. Okay? And this is the 3-hole sphere. Okay? Okay, now let's talk about maybe taking a ribbon and twisting it once. Okay, and you, again, go through here. And I see 2 holes. The boundary elements have 2. There's 2 of those boundary elements. Okay, so it's 2-holed. And then I think about this. This is, notice that if you're going here, like here, and then you go around, you get kind of flipped over. This is an unorientable surface. So it's a 2-hole, what we call, this is by Princeton, who's Conway's name for these things, the 2-hole cross surface. Yeah, but he introduced the cross surface, and Bill likes to change names of things, so I'm going with Bill on these things. All right, so another one to do is to introduce 2 of these, and this you'll see, okay. That is also non-orientable, okay, because if you go around here, this turns around like this, and then you go back over here, it's the opposite orientation. If you think about here, you're turning it around. So this is, and it's a 1-hole. There's only 1 hole because there's only 1 boundary component. So it's the 1-hole Klein bottle. Okay. And the last one is the one that's going to be of interest to us. We introduce this cross, little twist for everything. Again, there's only 1 hole to this, yeah, is there only 1 hole? Yeah, because you go around, come up, around. So it's 1 hole, and since it has to be a surface with 1 hole, and it's orientable, because as you go, if you have an orientation here, you go back. Any way you want to go back to the top, you're going to switch the orientation, so it's going to be orientable again. So it's the 1-hole torus. Okay? All right, so in all of this story, this was a while ago. This is what I'm going to do later. We did this a while ago, this a little while ago, and this is, well, we've known it for a while, but this is just coming out this year. This is what I'm going to talk about later. this is the thing that's not, we know what's going on here in the with one whole torus, but we're not sure. Okay, we're not exact. We don't know how to write it up yet. Okay, all right. So we're going to hit these two and this third one, and I'm going to leave this case. Okay, so first of all, so this is the kind of the topology picture, and of course I want to also think about the hyperbolic plane picture, hyperbolic 2 geometry. And so how do you get, and I like to think about my hyperbolic plane as the Poincare disk. How do you get the Poincare disk model? You take a transformation like this, and a transformation like this. Okay. It doesn't matter that they go opposite of each other, but there's reasons for me to do that. But anyway, this is, and if you think about the H2 mod, and this is a group, maybe this is a generator A, and this is a generator B, and this is maybe A and B are the axes of these hyperbolic generators. Okay, this is H2 mod, the group generated by A and B. And you get a 3-hole sphere like this, right? Well, the holes, let me just show you where the holes are. Here's one hole, right? Here's one hole, because you come across here, you go down here, you go back, and then that's one of the holes. What's the other hole? These two points are identified. This is the blue is the identification. It takes that arc to that arc, and it moves it inside. Okay, and there's your other hole, right? It's like the hyperbolic plane, and you made this identification. Right, yeah, and you're making this identification, right? And here's your other hole right over there. Okay? Maybe we'll do another one just to show you what's going on. Should we do the one-hole torus just in case? Well, since this is actually, in some sense, this is the other one-hole torus. You take an element that takes this line to this line, right? That's A. And then down here, oh, sorry. And that's B, right? And so now, if you think about it, so what's the hole is going off to infinity, right? These points are identified to that one. That's where you get the pi 1, the one of the pi 1s, right? And so you say, well, here's the line right here. That's part of the hole. And then this is transferred over this one, right? Because this point is identified to that point. This point's identified down here, so that's the next part of the hole. This point's identified here, that's the next point of the hole, and we're back. And so there's your hole. There's your different arcs of your hole. So it's like picking out different arcs of these holes. So, I'm sorry, just kind of a dumb question. No, it's okay. I'm not really. Yeah. I'm sorry. So I've never seen this sort of hyperbolic picture. So this is like putting a hyperbolic structure on the hyperbolic. Yeah. You want to put a hyperbolic structure. This is a H2 geometry of these surfaces. Topologically is these other ones. Yeah. Here's the geometry, and it's the geometry that makes sense, right? In the sense that everything's regular, right? All points are essentially, well, yeah, they look at least locally the same. Of course, there are points that are on closed geodesics that don't look the same as the other ones, but locally they all look like a piece of hyperbolic plane. And you want these, and basically what you can do is talk about, this is kind of a ping pong lemma in a sense, and they call it the ping pong lemma because you kind of go between these little regions. And the idea here is that if you can find these regions so that the exterior of this curve is taken into the interior of this curve in the same way over here, and you can find 4 of these disjoint curves bounding a common region, then this is a proper action. This is a good action, which gives you a nice manifold, right? So this looks exactly like this. Topologically, it looks exactly like this. Okay? Yeah, A and B are isometries. They're maps. They're whatever they're. Okay. Let me just talk about a little bit about the unorientable cases too, because I always screw these up myself. So I make sure. Yeah, this one is. Okay. So we start with the same. Okay. Same picture here. And now this is A, and then this is B, but this is, and we're going to use this notation to mean that not only is it B, but it takes the manifold, and it's what they call slide reflection. Okay, it goes, it's moves it along this line, and then it reflects it. Right, that's the isometry. That's where you get the unorientable thing. Right. All right, and if you think about it, this will also give you two holes. This will give you two holes. We can, if you'd like to see the two holes, one of the holes is obvious. Well, maybe not obvious, because it takes a little bit of time to think about it. But this is one of the holes right there. That's one of the holes. And the other hole comes from these three arcs make the other hole, right? And it will do that, right? We'll start here. Go along part of the hole, and then where does that one get identified? That gets identified down here. To continue, you go that way on the hole, and then this one gets flipped down to here, and then this one is back up, right? And so you see the three arcs of the holes, right? And as you might guess, you do the same thing for the one-hole Klein bottle. Okay. But you basically you pick a you have crossing axes, if you will. These are axes, but and one of them is the same kind of picture as here, but you take one of them and you put a slide reflection instead of just a regular transvection, if the words. But all of these are H2 mod these groups, different groups. Okay. And they're all the same idea, right? Slightly different, of course. All right, so the isometries of H2, I should say the orientation preserving, let's just worry about the orientation preserving, although I know I did orientation reversing ones here, but let's just talk about the orientation preserving ones, are isomorphic to PSL2R. Okay, they're also isomorphic to something else. Okay, some other good, well-known group, and that's the identity component of SO21. Okay, and so a lot of this discussion can be placed in the context of what happens in R21, the natural space for R21. Okay, which is Lorentzian geometry. Okay, and so let's just talk about the geometry here first of all. The geometry goes like this. If you take the inner product between two spaces, it's the same as your inner product. What my wife has just described as an inner product, or this is not an inner product as far as she's concerned, but it is for me. It's x1, y1 plus x2, y2, and she doesn't believe in this x3, y3. Okay? She doesn't believe in that at all. So that's not an inner product. Okay, I would say hers was a positive definite inner product, or usual Euclidean one, and now we've got this other one. Okay? And you can see why we're interested in this and why this is part of the story. These surfaces are part of the story, because matrices which preserve this inner product between two things are these types of matrices, SO21. Okay? All right, and we should talk a little bit about this, in that there's kind of a classification of X in R21, but in the following sense: if you take the inner product with itself, if it's greater than 0, which is the usual thing you'd imagine, X is called spacelike. X is spacelike. And if it's equal to 0, X is called lightlike. Every once in a while I'll use the word null, but basically it's the same idea. And if it's less than 0, X is timelike. Okay? And the idea here is that if you look at what the set of light-like vectors, and it's the light cone, and you can imagine my speed of light, of course, because I'm a mathematician, my speed of light is 1. The other thing is, by the way, if you ever go to a physics talk and they ever talk about Lorentzian or Minkowski space, they always use the opposite notation. They'll use minus, minus, plus instead of plus, plus, minus. But we're mathematicians. I like more pluses than minuses. That's all. Okay? And so these are inside the light cone, they're the time-like vectors. Okay?
Does that make their time-like our space-like?
No, that's just they just to change the name. It's changed the name to protect the innocent. Okay. And outside here are space-like vectors, and I can tell you a little bit about that, but maybe not today, about what that means in the space. In basically, a path like this. If you're living in this world where you can't go faster than anything, you go up here. That's a time-like path where your derivative is in the direction of a time-like vector. That's a path that, quote unquote, you can do, right? Most things can do. By the way, for those of you who watch a little Star Trek, does anybody watch a little Star Trek? Okay. Do you know what a tachyon is? A tachyon is actually a thing, and it's something it's a beam, right? It's a thing that goes faster than the speed of light. So it's a space-like vector. Okay. A tachyon would be something like this. This would be a tachyon. It'd be a direction that you would go. And of course, no, it would be space-like. It's space-like. Because most things are time-like, right? Most things are time-like. You are time-like. You're not a tachyon, right? Okay. I don't know. I don't know about these guys. That's yeah. They have all these different theories. Yeah. There's a couple things I want to tell you a little bit more about this. There's a copy right here where if you look at the set of vectors such that their inner product with itself is -1, and something else, I'm going to talk about what that something else is. If you look, that's a two-sheeted hyperboloid. That's a particular version of H2, right? Where straight lines, where geodesics in this one are the intersections of planes through the origin and that hyperboloid. Just one of them, right? And a lot of times they do this projectively, so it's all, the bottom's the top and the top's the bottom. The other thing is there is something different between that and that. There's two different naps, right? There's two different components to this. And so you can choose this. This would be additional information. This is more than Lorentzian geometry. You can choose one direction to be the future and the other direction to be the past. Okay? And that's choosing one. Okay? All right. All right, so let's talk about what the isometries are. Isometries of R21. And I should say I'm cheating a little bit because I really want the isometries to be affine space. Now, what are the isometries? What are Euclidean isometries? If you remember what Euclidean isometries are, you hit it with a rotation or something like that, right? An O2 something, but then you translate it also. And so isometries of R21 are something that look like, in fact, we'll do the full one, O21, semi-direct product, R21, right? Where you say A and V, where that's an element of A and that's an element of, let's call it A, okay? Is equal to A acting on a space, a point X, AX plus A, right? All right, so let's get the dictionary here. Remember, we have this dictionary, okay, between PSL2R, or SL2R if you want, and SO21. Okay, the identity component of SO21. There are there are different types of isometries of these things. So I'm talking about just these, the linear part, the A part. And there's a classification of the isometries. And we can look at if something is equivalent to cosine theta, sine theta, negative sine theta, cosine theta. This is called elliptic. And it's just, and if you want to think about what it does on the hyperbolic plane, it just fixes a point and it rotates it around it, right? Depending on what the point is. Over here, what's happening in SO21, you have the same cosine, you have the same block as before, cosine theta, sine theta, negative sine theta, cosine theta, something like that, and then you have a 1 like that. It's not really that because I really shouldn't put it there because what's going to happen here, you can show, it's not obvious, but you can show that what's going to happen here is you're going to fix a line. Here we'll do it. And you're going to have a rotation around that line. Okay, you're going to fix a time-like line. That has to be time-like. It's not, it takes a little bit of work, but it's not so hard to show that that has to be time-like. Okay, and of course the other ones are parabolic. And parabolic elements look like something like 1, x, 1, 0, something like that. They're conjugate to that. Okay, and they look like, here, do it with blue. Okay, like that. Like that. It's where there's one fixed point on the boundary. Same idea over here. I'm not going to worry about it so much. Same idea. I'll tell you. But what the most interesting thing for us today, and just to talk about, is hyperbolic. Okay, and these are essentially something that looks like lambda inverse, right? And what do hyperbolic elements do? They do exactly what we're doing over here, these pictures, these individual ones, although there are examples of these that include parabolics too, but I'm not going to worry about parabolics today. And so it basically takes something like that, and it moves. And there's a fixed point, right? There's two fixed points for hyperbolic, and it moves that line to that line, and that's exactly what we're doing over here. Okay, so what happens in SO21? All right, let's see if I can draw it. Okay. Well, there's going to be not two fixed points, but two fixed vectors, right? Well, they're not really fixed. They're actually going to, we're going to talk about that in a second. But these vectors, look, there's going to be they're going to be eigendirections, so they're not going to be fixed. And what's going to happen is that instead of a kind of geodesic, what's the corresponding thing in the geodesic is this kind of plane through here, like that. Okay, do we have more color? Good. Can I can use more color? Yeah. Yeah, it is a cross section. It really is a cross section. It is exactly that because there's a hyperbolic plane up here, right? Now, I would say I'm much more attracted to the Kleinbile now in my old age, just because of anti-de Sitter space than I ever used to be. Anti-de Sitter space, which is related to all this stuff, than I ever used to be. So I never thought much of the Klein model, but in fact, that's the only one I can draw for anti-de Sitter space. Okay? Okay, and in here, and this one continues like that. And so the action is to go across, right? The action is to go across. It's like to move that. Move this plane to that plane. Okay? Now, okay. So now, this is just the classification of the linear part. This is the dictionary of the classification of the linear part. I can't even write my own, read my own writing up here, so I don't know. But of course, we want to consider all these, we want to find these other, we want to consider things that have an A on them, right? And so what we'll do is we want to consider A of x is equal to ax plus a. Too many a's, but that's the way it goes. Life goes on. Okay? I want to do with a lot of b's and stuff like that. So, okay. Now, going back to this story over here, whenever we're talking about the linear part, there's a classification of the linear parts that Sean really, really likes. Okay? Two elements which are conjugate have to share the same trace, right? And any two things which have the same trace are conjugate. So they're essentially, they might have different fixed points, but they're essentially the same one. You can make one look like the other by a conjugation. For any one of the, all the parabolics are parabolics all have the same trace, and they're all, yeah, they're two, yeah. But the absolute value of trace, actually, because there's, yeah. And I want to do something else. I want to do something that, I want to find out all the things which are conjugate now in this bigger group, right? Not just O21 or SO21, but I want to consider all these things that are conjugate in this bigger thing. And what I'm going to do is I'm going to introduce a new idea. All right, so let's assume, for the time being, that A is hyperbolic.
For that, you want x to be non-zero there, right?
What? Yeah, parabolic. X, yeah. X not zero. Yeah. Otherwise, it's the identity. Right. Yeah. Okay. Yeah. I know. You worry about that crap. No one else does. Let me just no. That's fine. Let's just give you grief. Okay. I know. Doesn't he? Oh, maybe that's me. Okay. So let's think about this a little bit more. Okay. And so what we're going to do is I'm going to draw this idea, right? And okay, a hyperbolic element. So it's this sort of thing, right? And I'm going to actually worry more about what these things are, right? There, we have the one that goes with the expanding. This is the expanding. Oh, no, let's get this to be the contracting one. Contracting. So lambda is less than 1. Okay? It's the eigenvector that goes with that. It has to be null. Now, if you think about it, why does it have to be null? Because it's contracted or expanded. It's the same direction. If it's not null, then it's going to change the length. Right? And you can't change the length. And so this is the expanding eigenvector. Okay? And I'm going to choose them to be on the same nap, which is a Lorentzian thing. I'm going to choose them to both on the same nap of the thing, or the same, both of them to be in the future. You can actually choose whether they're both in the future or both in the past. It doesn't really matter, but let's just do it in the future. And I'm going to call this to be A minus. This is A minus, and this A plus. So expanding, contracting. Right? So there's an eigenvector. These go with the, this is the eigenvector that goes with the eigenvalue which is positive. And this is the eigenvector that goes with the eigenvector which is negative. There's also another direction. Again, you can show, it takes a little bit of time, but it shows it in, it has to be perpendicular to Lorentzian perpendicular, right, to that element. Everything has to be, the dot product with A naught and A minus and A plus and A minus have to be 0. Okay? So this is space-like, and it's the direction that you go. Right? And there's a way to choose this. There's a way to choose this is that you say A minus cross A plus, and this is the Lorentzian cross product. Dot A naught is greater than 0. Okay, there's a direction that you can choose it. Lorentzian cross product is the same as the other one, except there's a minus in the third direction, right? It's the same formula, right? It's the same exact formula. It comes from the determinant. It gives you the determinant with this inner product. So you need a minus. So it's like, you know, whatever that is, I always forget it. I have to work it out myself, you know, just like everyone else does. And that gives you a direction to this A naught. By the way, you can choose A naught dot A naught equal to 1, because it makes sense to say, well, what's the length of that A naught, because I have an inner product. You can't really choose the length of A plus and A minus, but you can say they're of some length, right? You can impose lengths on it, but it doesn't really mean anything Lorentzian. Okay, so Margulis comes along. He knows all this. He knows a lot of crap, that man. Okay. And he thinks about well, I don't know if he thinks about this, but he thinks about what does A look like? Okay? He thinks about this. And if you take R21, you take a space like this, and you mod out by just the cyclic group, right? Okay. What's going to happen is that, oh, I forgot to tell you the one thing in here. If you look at A has a unique invariant line parallel to A naught. You can show that there's a unique invariant line. It's a linear algebra proof. It's not so hard to prove. So somewhere in here, whatever that A is, it's hyperbolic. There's a unique invariant line that's parallel to A naught. So when I factor it out, and let's just assume that there's no fixed points, we'll do that, is that basically you have this A, you have a transformation. Here's that C alpha, right? Call it C A. Right? That's a unit invariant line. And when you mod out by R2, 1 mod the group generated by A, you're going to get a closed geodesic, a unique closed geodesic. Just like when you mod out by this, you get a unique closed geodesic on the surface. Right? What was related, Sean knows this, I hope. What was related to the length of that hyperbolic thing? The trace, right? The trace told you what the length, well, it's related. It's not exactly, it's a cosh or some crappy thing like that. Who knows? Yeah. Cosh. It's cosh. It has to be cosh. Or our cosh or whatever. I want to figure out what a length here is. Okay? So what I'm going to do is I'm going to take an x on this invariant line. I'm going to look at how far A moves that, and then I'm going to dot it with A naught, because this is in the direction of A naught and A naught units. Well, this is fixed by so it takes this, so A, the script A, the affine A, moves everything along this line. Oh, I see. Right? Yeah, I see what you're saying. Right, it's an invariant line, yeah. Okay, right. Yeah. Right, okay. Yeah. Okay? Yep. Yeah. I think that's what. This is going to be called the Margulis invariant, or the alpha, or whatever. I forget what we call it half the time. It's this length. Okay? Shocking things happen with this, because Margulis was trying to prove that you could never find one of these Lorentzian groups which act nicely on this space. Okay? And he... It gives you a distance, yeah. Ah, okay. So there's a bunch of comments that we can make about this alpha, right? The first was it's independent of choice of x. If you pick an x off the line, and you look at the well, you have it's kind of swooping, right? Because it's contracting, but all of that motion is in the a plus and a minus direction, which when you dot it with a naught is perpendicular to a minus and a plus. When it doesn't notice that, so it doesn't notice the swooping. Oh yeah, it doesn't matter, and on it's certainly true because it is just a translation on this. But even off of it, it doesn't matter. Okay, and equal to 0 if and only if a fixed point. Okay. What are the other? I forget the third one. Yeah. Well. Yeah.
You don't have any minus contributing, like your metric, your dot product is really
Yeah.
positive definite.
Right.
Right.
Yeah.
I think that's
Yes. Yeah. You could have picked a point again. If there's a fixed point, you could have picked a point that's not fixed. But again, where would all of its motion would be in the a plus a minus direction, so it would be perpendicular to that. Yeah. The most interesting thing is the third point, which is alpha of a to the n is equal to alpha of a to the n, alpha of a. Okay, that's not surprising. That bothers me a little bit. That n bothers me a little bit. In particular, n times, yeah, it's n times that. Absolute value of n, yeah. So in particular, what's in particular? Okay, alpha of a of alpha inverse. What's the thing for in particular? E.g. Okay. Alpha of alpha a inverse is equal to alpha of a. Okay? Now think about that just for a minute, because along this line, what does the inverse do? It moves it backwards. Okay? But what happens here is that but what happens with the a plus and the a minus? A plus and a minus for the inverse are opposite, right? So a naught points in the opposite direction. So it's the same alpha, right? Okay?
But how is a naught coming in the opposite direction?
Well, a naught of a inverse, right? Here's a minus a plus, right? And that's a naught. This is a inverse plus a inverse minus, and so that's a inverse naught. And so even though you're going in the opposite direction, it doesn't work, right? It's the same thing. Okay? It's where the absolute value, yeah, it's the absolute value of n. And that was the most important part of that. It's kind of clear that it's going to be n times it, or positive something times it. Something that's linear compared to n, but it wasn't clear. It's not necessarily clear. You have to think about this. This actually shows up weirdly in higher dimensions, which is really nasty. Why a lot of this stuff expands to SO43, but does not work in SO32. So, which I haven't told you about, because I haven't told you the most important thing that Margulis did with this, and that was the opposite sign lemma. Opposite.
What are the geometries for 4, 3, and 3, 2?
I don't know, 4, 3, and 3, 2. There's 7 to right. Yeah. That signature. Yeah. Okay, so the opposite sign lemma says if you have alpha A and B with alpha of A and alpha of B different signs. Okay, so if they have opposite signs, then the group generated by them does not act nicely on your space. Okay, it has lots of accumulation points and stuff like that. It doesn't act properly. Does not act.
You're assuming both that A, the multiplicative factors A and B are both parabolic?
Hyperbolic for the time being.
Oh, yeah.
Okay. Yeah. Now, okay, I'll tell you, let me just add a few more. I'm never going to get to where I wanted to go, but that's okay. Okay. Elliptics never come into play. You never really have elliptics. You can't join two elliptics because there isn't really a defined alpha for that. You don't have a defined sign of the alpha. It doesn't really make any sense if you think about it. Too many rotations in the same direction. It doesn't make any sense. Parabolics do. You can define a direction for parabolics. Okay? And that was done. So the parabolic case, parabolics, same thing happens. Same things happen. True. Case done by Charette and myself. Okay. All right. In fact, Laborie now says it's the Charette-Drumm Margulis invariant, which we like when Francois says those things. Puts, we like to throw in with Grisha, it's like, yeah, we're okay. Okay, so all of this is to say, now, the other thing that to say is any two, if I fix the linear part, let me just say this instead of writing it. If I fix the linear part, any two transformations with the same alpha are conjugate. So in some sense, this is kind of taking the place of trace. This is expanding the same idea as trace. This is kind of a trace because it's related to the length of the geodesic, right? It is the length of the geodesic. And two things with the same alphas have the same trace, given that their underlying linear part's the same. Okay? Which is not necessarily obvious, but it takes a little bit of time. Okay? All right. Okay, so okay. By the way, well, no. Let's talk about this. Okay, so what's the whole point of this? Is that Margulis actually got these examples of these things, these affine transformations, the Lorentzian transformations, which do act properly on all of three space, R21. He found them. Okay, we'd like to find them, but we'd like to put a little bit of geometry on it. Maybe make it look like these manifolds over here. Okay. So we'd like to take these fundamental domains that we have over here and translate them into Lorentzian.
Is that an nullius statement?
Which one?
The opposite sign of
No. It just, yeah. No. In fact, definitely not. Definitely not. It is in certain things, but we'll talk about it when it is. But it's not. It's definitely not. Okay, so the idea here for all of what Bill is talking about, half of what Bill is talking about, is all to say, what do these manifolds look like, and what can we, given these geometric objects, can we figure out what they look like? So the idea is to take a geodesic in H2 and extend it up into Lorentzian space. And maybe you've seen this before. I've seen it in my mind maybe a billion times. Okay. And it's that picture that I just drew here. Is that now I want the analog to geodesics in H2 in R21. Now there is one analog is just a plane, but that's not going to be that interesting for us. We want to be able to combine them in a sense. So what I'm going to just draw the first one, okay? And I know what a geodesic looks like, right? It looks like this part, right? There's a part. Okay. All right. And the key part of this is now, for many reasons, which will maybe come obvious later, is we're going to look at half planes emanating from this. So we'll go like that direction. And this one is in the back, so it goes out like that. This one goes out like this. This one comes to the front. Okay? And that's going to be the analog to the geodesics in Lorentzian space. You got to stop me. I don't even have any clue what time it is. So, yeah.
You got it. It's 3:23. You got to know.
Okay. Oh, okay. That's a crooked plane, right? And these are actually Sean printed them out, but J.P. Burrell at University of Maryland sent him the thing. I have a copy of these too. And this is what the crooked plane looks like. That's what the plane is, right? These are actually two crooked planes. It's kind of in between two crooked planes. There's the plane. These are called the wings. These half planes that go off to infinity. And these things are called the stems. Which, by the way, I talked to Lisa, Toronto Lisa. Jeffries. And she says, that's really screwed up. That is really screwed up. Wings are butterflies and stems are flowers. And she was very upset by that. And I thought, she's got a point. That's the worst part about it. So the idea about all this, which I did not get to at all, but that's okay. I'm not, yeah. The idea behind all of this is that we want to figure out which groups act nicely on space by looking at whether we can build these fundamental domains or not. Whether we can find disjoint ones. Now, one of the things, yeah, the whole thing is the fundamental. This is the geodesic. This is the geodesic. Now, if you take two like this, you can see it's pretty obvious. Well, you just separate them like that, right? There's a direction that you can just separate, and they're not going to intersect. And so now you do 4 of them. You do 5 of them. You can do any pair, and you can do that same thing. Okay? Now, I've known this for like 17, 18, 19 years.
Are there like some findings that are fitting together here?
Oh, yeah, they're all paired. But you can imagine a lot of them. You could have 100 around there. Just so that as long as they have 100 different arcs like this, from different arcs like this, you build them, and then you take, if I translate this one by this a vector and translate this by a vector, I can always find another vector, an A, such that moves this crooked plane to that crooked plane. What's the most amazing thing about this all is that these aren't the most wonderful crooked planes to look at. That's due to, although in a paper with other people, it's really done to Virginie Charette. She figured out how to do this in a really cool way, and it's really disturbing. And maybe I'll tell you that some other day, but it's really too disturbing for this type of time. Yeah. Okay. So I'll tell you the gist of it. You can classify things. You can actually do what the hard part is. It can move all around. You could say, "Oh, how could you classify this? How could you hope to classify it?" What she did is she realized, like for instance, let me give just an example where you have a 3-hole sphere, right? Okay. So you have a translation like that, and you have a translation like that. And she said, "Well, what we should do is not look at the fundamental domain for the entire space, but look at, I forget what it's called, right? Oh, it's this one, right? It's this one. Right? It's the fundamental domain for everything outside of here. It doesn't cover the whole thing. But from here, it has enough structure that we can actually do calculations, and these are amazing. It works. It still ticks me off to this day. I still have memories of traveling on Amtrak and saying, "No, it can't be right." And her last comment to me that convinced me was, "I'm just quoting you your theorem." The meanest thing she ever said to me. I'm just quoting you. But anyway, she used this, and we can actually find this thing. This for the the title of the talk was about the one-hole torus. That mimics the fairy triangulation of the triangles that you get. We get triangles like that, and we mimic the fairy triangulation of this. But anyway, we answered most of Rebecca's questions, which were most of, no, that's great. That's
During the time, we'll take further questions out in the hallway.
Or allow people to come in.
Or you could ask. Yeah, that's right. Let's open the door.
Here, but
I'm gonna go ahead and shut the camera off.
yeah, that's not going to sound good at all.
Okay, very good. No, it was great talking.
that was a lot of fun.
Yeah.